To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today I am going to discuss with you all electromagnetic induction. Now in the previous chapters, initially we discussed what magnetism is. So there you were able to understand the permanent magnets and the electromagnets. Electromagnets, when current passes through a conductor, there is magnetism induced. So there, to identify the direction of the magnetic field, you can remember we use the corkscrew rule and the right hand grip rule. Thereafter, you all were able to understand if we place a conductor in a magnetic field, and when current flows through that conductor, there is a force generated. And this force, the direction of the force, was determined using the Fleming's left hand rule. And based on that concept, we've looked at different devices. For example, the direct current motor, then the loudspeaker, and also you can remember even the analog voltmeter, ammeter, they are also based on this particular principle. So that is what we discussed in the previous chapters. Now what we are going to discuss here under electromagnetic induction is just the opposite of what we discussed previously. So here of course what is going to happen is we have a magnet and there is a force, there is a conductor placed between the magnetic field and we apply a force or there is movement, and because of that movement there is electricity generated. Due to magnetism, there is electricity generated. Or really if we try to understand it, you will see when there is a change in the magnetic field lines, there is electricity generated. And that is what is known as electromagnetic induction. So we studied the motion caused by electricity in the previous section. So you can remember motion caused by electricity in the previous section. So that is the force I told you. We will next focus on producing an electric current by a conductor that is moving in a magnetic field. So that is important. An electric current produced by a conductor that is moving in a magnetic field. So when there is a current flow through a conductor placed in a magnetic field, a force is exerted on the conductor causing it to move. So this is what we discussed before. When there is a current flow through a conductor placed in a magnetic field, a force is exerted on the conductor causing it to move. That is what happened in the dynamo. So you can remember the previous example, what I told you all about the direct current motor. We have the magnetic poles. You can remember that, students. Like this, we had the north and south. Like this, we had the magnetic fields. Then we had the wire coil. So here we had the magnetic poles. Then we had the armature. And then we supplied electric current. So when current flows through the wire coil, that is placed between the magnetic field. You can remember there was a force generated, and because of that the armature rotates. So that is the direct current motor. That is what we have discussed so far. But now we are going to discuss the inverse or the opposite of this effect. Here of course we will have magnetic field, but there will be motion, and due to that motion current is going to be induced. That is what we call as electromagnetic induction. Unlike in this one, it's going to be the inverse or the opposite. So here electromagnetic induction is the inverse of this. That is, if a conductor placed in a magnetic field is set in motion, then an electromotive force is created between the terminals of the conductor. So, you all can understand that. If a conductor placed in a magnetic field, so we have a conductor in a magnetic field and there is motion, then of course electromotive force is created between the terminals of the conductor. The generation of an electromotive force between the terminals of a conductor when the conductor is kept at rest in a changing magnetic field or when the conductor is moving in a constant magnetic field is known as electromagnetic induction. So, this is something that you all have to remember, students. So, this is important. Now, what they mean here is the generation of an electromotive force. So, here electromotive force has to be generated. So, between the terminals of the conductor, but there you can have the conductor at rest and the magnetic field can change, or you can have the magnetic field fixed and the conductor can move. Either way. So, we will be actually looking at two types of dynamo. There you will be able to understand both these instances. So, if you have a magnetic field, say you have the north and the south poles, and if there is a movement. So, again if you have a copper wire coil and if there is rotation or movement, there is magnetic field, there is movement, because of that current will be generated. So, here of course the magnetic field is fixed, the conductor is moving. In another instance, we can have a magnetic field, say north and south, moving around a conductor. So, something like this. This is just the diagrammatic representation, students. So, here also when the magnetic field is changing, magnetic field changes. Around a conductor, then also the conductor is but at rest. Then also electromotive force is generated. So, both come under electromagnetic induction. So, what you need to understand is that there should be a magnetic field and there should be movement so that the magnetic field lines vary. There is a change in the magnetic field lines. Then only there will be electromotive force generated. So, we will discuss that in more detail after this. With that, I am going to move on to the next slide. So, here, if we look at electromagnetic induction, you can see the diagram here, Michael Faraday. He is the scientist who first introduced electromagnetic induction. So, here we can say electromagnetic induction was first introduced to the world by Michael Faraday. So, that's important. An important law known as Faraday's law regarding this was presented by him in 1831. So, this Faraday's law is related to electromagnetic induction. Calculations related to electromagnetic induction. So, Michael Faraday is the scientist who introduced electromagnetic induction to the world. So, you can see his picture here. Then, the phenomenon of electromagnetic induction is used in magnetic cards. So, you are familiar with magnetic cards. So, here you can see this is a card machine. Normally, we call it as a credit card machine or a card machine, where when you purchase something, when you purchase goods, you just swipe the card through this machine and you can pay for your goods. So that is how the basic function is. So this particular card, you all know, has a black color band like this. That is magnetized. So that is why we call them as magnetic cards. There the information is stored based on electromagnetic induction. So when you swipe the card through this machine, that information can be read by the machine. So magnetic cards as examples. We use these cards, employees of different offices, shops or offices where you use the magnetic card, they use this card. Then the credit card, debit card, ATM cards used by banks, the customers of the banks. So those are also magnetic cards. So you can see the phenomenon of electromagnetic induction is used in magnetic cards used to enter shops and offices by employees, and the magnetic cards, that is credit and debit cards, used to make payments. Electricity, essential for the daily activity of the modern world, is mainly generated by converting the energy produced from sources such as oil, coal and nuclear power into electric energy through electromagnetic induction. So this is also something you all have to keep in mind, students. The electricity that is generated. Now, when we say electricity that is generated, you all know there is the hydropower plant, thermal power plants, nuclear power plants, coal power plants, like that. By different methods, we generate electricity, even windmills. Now, if you take a hydropower plant, you all know that the water stored at a higher elevation flows down, and when that flows down, it falls onto a turbine. And there the turbine rotates, and due to this rotation of the turbine, there is electricity generated. So there is rotation, there is magnetic field, and due to that electromotive force is generated. So although we use different methods like oil, so this is also something you know, oil, coal and nuclear power or even hydropower, in all these, electric energy is generated by electromagnetic induction. So that is something you all have to remember. So the uses of magnetic cards, employee cards, bank cards, all those, as well as electric power generation, they all use the principle of electromagnetic induction, which was introduced by Michael Faraday. So with that, students, I am going to move on to the next slide. So here we have an activity to understand electromagnetic induction. Activity: demonstrate electromagnetic induction. To do this, we have these apparatus. The apparatus required, we need a magnet, a bar magnet, Now, when we have a bar magnet, and then we need an empty reel of thread or any insulator material. You can even use a PVC tube. So any one of those, a cardboard cone-like structure. So any one of those can be used, but we have to make sure that the magnet, the bar magnet that we are using, can move through this tube easily. So that is how we need the bar magnet and the empty reel of a thread. So then what we need is, we need copper wire, copper conducting wire. Then we need the galvanometer. So we need the galvanometer. So those are the materials. We need a bar magnet, an empty reel of thread, then copper conducting wire and galvanometer. So those are the materials. We'll move on to the next slide where we look at the procedure. So here we have the method. Now here you can see, look at the diagram first. So here you can see we have that reel, empty reel of thread, or like I said, we can use even a PVC pipe and all that. So around that, what we do is we wind the copper wire into a coil, like shown in this diagram. And the two ends of the copper wire, normally we start the winding process from the middle of the wire and middle of the reel, and then the two free ends are connected to the galvanometer. You know why we use the galvanometer? To detect the current flow. So once you have made the wire coil, then what we do is we take the two free ends of the copper wire and we connect it with the galvanometer. So now this part of it is ready. Then what you do is you have the bar magnet here. What we do is we hold the bar magnet near the wire coil. Then we move it. After this activity, at the end of this activity, there is a table given to you in your textbook where they have given different steps, actually up to step 9. So there they have specified how we should move the bar magnet and the coil. So we do those steps and observe the galvanometer. Now you all know, students, if there is a deflection in the galvanometer, that means there is current flowing through this conductor. So if there is current flowing, now there is no power source. There is no source to supply electricity or to provide electromotive force. So that means when we are moving this magnet with the or near the or into the coil, if there is deflection in the galvanometer, you all know that there has been electricity or electromotive force generated. So that is what we can understand from this activity. So here, if we look at the steps, form a coil by winding the copper wire around the thread reel and connect its two ends to a center zero galvanometer. And the purpose of using center zero galvanometer, you all know one thing, to observe the deflection and to identify that there is current flowing, and also from the direction of the deflection, you all can identify the direction of the current flow. That is very important. That is why we use a center zero galvanometer. Now, do the movements given in the table below and fill the table by observing whether there is deflection in the galvanometer or not. So, do the movements and fill the table. Observe the relative magnitudes of the deflections in steps 8 and 9. So, you do up to 7, and in 8 and 9, you need to observe the relative magnitudes of the deflection, whether the deflection is faster or slower. So that is what you need to observe. So before I do the activity, I will show you all the table also. Then you will know how we need to do the movements. So for that, I'll move on to the next slide. So this is actually for the observation, this table. But here you can see motion of the magnet, motion of the coil, and this is what you need to fill up, whether there is a deflection in the galvanometer or not. So here, what we do is we have the coil stationary. You move the magnet towards the coil. The next step, you hold the magnet stationary near the coil while the coil is also stationary. Then third step, you move the magnet away from the coil while the coil is stationary. So initially you have the coil stationary, bring the magnet closer, hold it there and take it away. Then here you can see the next two steps, the magnet is stationary. You hold the magnet and you move the coil towards the magnet and you move the coil away from the magnet. Then also you observe what happens. Then what we do is we move the two, both the coil and the magnet, away from each other. Thereafter, towards the coil and away from the magnet. So what we do is we hold the magnet and the coil at a particular gap and you move both of them together. That is towards the coil and also this is away from the magnet. So they are both moving simultaneously. Then also you observe the galvanometer. Then these are the steps 8 and 9. There what we do, rapidly towards the coil. That is, coil is stationary but you are moving the magnet rapidly towards the coil and slowly towards the coil. So these are similar to the first step. But what we do is we change the speed. That is why they have said to compare the magnitude of the deflection. Is that clear, students? So these are the 9 steps that we need to do during the activity. So there, I'll move back to the activity slide. So here, this is the method you have understood. Now you can understand. We have the bar magnet there. So initially this coil is going to be stationary. You take the bar magnet towards the coil. Hold it there. Then move it away. Then you hold the bar magnet, bring the wire coil towards it, move it away. Then you move both of them simultaneously. Thereafter, you move the bar magnet faster towards the coil and finally slowly towards the coil. Is that clear? So then you have to observe the galvanometer in all instances. I'm sure you all have understood this activity. So let's go to the lab and do the activity now. Okay, students. So now I'm going to do this activity in order to understand the electromagnetic induction. So to do that activity, here I have a magnet. Now you all can see the north and the south poles of the magnet. This is a bar magnet that I'm going to use. Then here you all can see, now normally we can take a reel of a thread and around that we can coil the copper wire, insulated copper wire. But instead, you can see here the copper wire has been already coiled. This is an apparatus made for this particular purpose. So here you can see the insulated copper wire coil and here you can see there is space. So this again acts like a reel and on this side also you can see it's a opening space through this so that we can insert the magnet this way. So it is similar to a reel. And we have the copper wire coil. And here you can see the connecting wires are connected to the center zero galvanometer. You all know why we use the center zero galvanometer. We can observe the deflection in both directions. So from there you can understand how the current flows and also you can understand whether it is alternating current or direct current. That means whether the current flows in one direction or in two opposite directions. So that can be understood from this galvanometer, the center zero galvanometer. Then I have the table here, what is given in your textbook, how we are going to move the magnet or the coil or both together, and then we need to observe the galvanometer. So here you can see motion of the magnet, motion of the coil, and whether there is a deflection in the galvanometer or not. So here you don't need to really record in which direction the galvanometer deflects. You just need to see whether there is a deflection in the galvanometer or not. So first, if I take the magnet, you can see towards the coil. So I have to move the magnet towards the coil. While I do that, you all have to observe the galvanometer. So here I am going to move the magnet. First one, we need to move the magnet towards the coil. Then you all have to observe the galvanometer. Now can you see? When I push it in towards the coil, you can see there is a deflection. Observe clearly, students. When I am moving it in, there is a deflection. But when I keep it stationary, there is no deflection. When I bring it out, you can see there is a deflection in the opposite direction. And when it is outside, there is no deflection. So you have to note that. As the magnet cuts across through the coil, we are not cutting it across, but as it moves through the coil, you can see a deflection. Again, observe. As I move it towards, a deflection. If I hold it inside, no deflection. When I bring it out, again a deflection. But when I hold it outside, there is no deflection. So, if we record that here. Now, when I move the magnet towards the coil and the coil is stationary, I did not move the coil. What happens in the galvanometer? There is a deflection in the galvanometer. Now, when I have it stationary near the coil is stationary, magnet was also stationary. There was no deflection in the galvanometer. And when I move the magnet away from the coil and the coil was stationary, then also you were able to see a deflection. So, only when there was movement, either towards the coil or away from the coil, there was deflection. And the other thing you all were able to note, when I move it towards the coil, the deflection is in the negative direction. When I bring it out, the deflection is in the opposite direction. That's the positive direction. So, depending on the direction of the movement, the deflection direction also changes. Those are the things you all need to observe. Then the next one, we need to hold the magnet stationary and I need to move the coil. Here you can see magnet has to be stationary, the coil has to be moved towards the magnet. Then again when the magnet is stationary, I will move the coil away from the magnet. So we will do that now. I'm going to hold the magnet, the coil I am going to move. Can you all see? As I moved it, there was a deflection. Now I am holding it, there's no deflection. When I pull the coil away, can you see? Again there was a deflection. When I move the coil in, there's deflection. When it is still, there is no deflection. When I pull the coil away from the magnet also, there is deflection. And you all can see the deflection occurs in opposite direction. Again, I'll repeat it. I am pushing the coil towards the magnet, holding it there, pulling it away from the magnet. Did you all see the deflection and the change in direction? I am sure you all did. So here, when the magnet is stationary and the coil is moved towards the magnet, there was deflection. Again, the magnet was stationary and the coil moved away from the magnet. There was deflection in the meter. Is that clear? Then, we move the magnet away from the coil. At the same time, the coil is also moved away from the magnet. So then what we do is we move both the magnet and the coil without changing the distance. So before that, what I will do is I will move both of them away from each other. Now, if we have it like that, if we move away, now when it is close, you move both away, still you can see a deflection. Now it's close here, I'm moving both simultaneously, towards and away. Then also you can see there is deflection. So when the magnet is away from the coil and the coil is away from the magnet, there is deflection. But if we hold them at a distance, so even though the magnet and the coil are close to each other, still if you move them without changing the distance, then there is no deflection. So what can you understand there? The distance has to change. The magnet has to go through the coil or away from the coil. If the distance is the same, then there is no deflection. So here, there is no deflection. Then, we need to move the magnet rapidly towards the coil while the coil is stationary. So again, I'll keep it stationary. I will move this rapidly. Earlier, I just moved it slowly like that. Now, if we move it rapidly, can you see? With the rapid movement, you can see the deflection. and you see the deflection is more. When I move it fast, the deflection is more. If I move it slowly, what can you see? So then if we do it very slowly, what will happen? Can you see? There's a small deflection. When I pull it out also, there's a small deflection. Again, if we do it slowly, the amount of deflection is less. But if I do it fast, can you see that the deflection is more? So what can you understand there? When we move rapidly towards the coil, there is deflection, more deflection. But when I move the magnet slowly towards the coil, there is deflection but less. So from all these, what can you all understand, students? When the magnet and the coil are stationary, there is no deflection in the galvanometer. So deflection in the galvanometer means there is current flowing. Now a magnetic field, a copper wire coil. And when there is a movement in the magnetic field, when we move the magnet, there is a movement or there is a difference, variation in the magnetic field. When there is a variation in the magnetic field, there is a current flowing. And when the variation is high, when I move the magnet faster, the current is more. When the variation is less, that is when I move the magnet slowly, the current is less. And also you can see, depending on the direction of the movement, the current is flowing in opposite directions. So here you all were able to understand, students, when I move the magnet towards the coil, deflection is in one direction. When I move it away from the coil, the deflection is in another direction. The same goes for the coil also. When the magnetic stationary but the coil moves, there also you see the deflection. I will repeat it once more just for you all to observe it and then you can understand clearly. When I move it towards, there is deflection. But if we hold it inside, no deflection. When I pull it out, there is a deflection in the opposite direction. When I hold them still, there is no deflection. Same goes for the coil also. If I bring the coil, there is deflection. When I am holding it, no deflection. Move the coil away, there is deflection. And if I do it fast, the deflection is more. So those are the observations you all need to understand from this activity. So here, using a magnetic field, we are inducing a current. And that is what you call as electromagnetic induction. Okay, students. So you all were able to observe the changes in the galvanometer. So you can remember during the activity, like mentioned in the table, I carried out all these steps or all the different types of motions. So initially we had the coil stationary, move the magnet. Then we had the magnet stationary, move the coil. Then we moved both the coil and the magnet simultaneously, like these two steps. And thereafter, similar to the first step, we had the coil stationary and moved the magnet, but with different speed, rapidly and slowly. And there, in some of the instances, you were able to see the galvanometer deflect, and in some instances, there was no deflection. So you can remember when I did the activity also, I filled up this table. So I'm going to fill in the same observations. Now you can remember when the coil was stationary and the magnet was moved towards the coil, there was deflection. So I'll use a tick to indicate the deflection. Then when the coil was stationary and the magnet was stationary, there was no deflection. Here, no deflection. Then after that, when I moved the magnet away from the coil, there was deflection. You can remember that. So that is what I marked in the table also. Thereafter, when the magnet was stationary and the coil was moved towards the magnet, there was deflection. And when the coil was moved away from the magnet also, there was deflection. There also, if you can remember students, I held the coil stationary also near the magnet. Then also there was no deflection. So from these observations, you can see only when there is a movement, either the magnet has to move or the coil has to move, there was deflection. When both magnet and the coil were stationary, there was no deflection. I'm sure you can understand that. Then we moved the magnet away from the coil and the coil away from the magnet. Then what happened? There was deflection. There was deflection. So when I had it close to each other and when I moved it, as I moved it, there was deflection. But once it was far away from each other, there was no deflection. You can remember that. Then the magnet was moved towards the coil and the coil was moved away from the magnet. So that is maintaining the gap between the two. We moved both of them together simultaneously. Then also there was no deflection. Then after that, what did you all see? When we moved the magnet rapidly towards the coil and the coil was stationary, there was deflection and a larger deflection. The magnitude of the deflection was larger than the first step. Then when we moved the magnet slowly towards the coil, while the coil remained stationary, there was deflection, but smaller deflection. So those were the observations. So from these, what can you understand, students? From all these observations, like I told you all, look at the instances where there was no deflection. Here, the magnet was stationary, coil was stationary. Here there is movement, but both of them, the gap was the same. Is that clear? So here there was movement, but the gap between the magnet and the coil was the same. In all the other instances, there was movement and there was deflection. Now, when you have the coil and you are moving the magnet, what happens is the magnetic field lines are varying. So, when the magnetic field lines vary, there is an electromotive force generated. And that gives rise to a current flow, and that current flow generates a deflection in the galvanometer. You were able to see that. So, only when there is movement either by the magnet or the coil. So, when the magnetic field lines were changing, varying, there was current generated. So, when both of them were stationary, there was no change in the magnetic field. The same way, when both of them were moved with the same gap, a fixed gap, then also there is no change in the magnetic field. So, because of that, there was no deflection. And when we increase the force of movement, rapid movement, there was a larger deflection. So, if we move it with a higher force, there is more electromotive force generated. When the magnet was moved slowly, the deflection was smaller. So, the deflection or the magnitude of the electromotive force depends on the speed of motion as well. Is that clear, student? So, those are the things you need to understand here. Now, when the coil or the magnet moves, resulting in variation of magnetic field lines then there is induced electromotive force. Electromotive force. This causes a current to flow through the galvanometer. That is why there is deflection in the galvanometer. The other one that you need to understand, the magnitude of the EMF. You all know what EMF is? Electromotive force. EMF depends on the speed of motion. So that is what you can understand from this activity. So we did the activity where we had the coil and the magnet. We moved them in different ways and we got these observations. From that, you were able to understand that when the coil or the magnet moves, resulting in variation of magnetic field lines, then there is induced electromotive force. This causes a current to flow through the galvanometer. That is why there is deflection in the galvanometer. That is one understanding. In addition to that, you were able to understand that the magnitude of the EMF, that is the electromotive force, depends on the speed of the motion. That is speed of moving the magnet or the coil. So that is what we understand from this activity. With that, students, I'll move on to the next slide. So here we can see, it can be seen from the above activity that there is deflection in the galvanometer for every motion where there is a change in the relative distance between the coil and the magnet. Important. So here that is important. You can see there is deflection in the galvanometer for every motion where there is change in relative distance between the coil and the magnet. So only when there is a change in distance, there was deflection. So that is why when we move both the coil and the magnet simultaneously with the same distance between them, there was no deflection. You understood that. But when we move them away from each other, there was deflection. So then, the galvanometer produces a deflection when there is a current passing through it. That you can understand. In order to create a current, there must be a source of electromotive force in the circuit. However, there is no such source in the circuit above. So in that activity, we didn't have any source of electromotive force. So because of that, the electricity or the electromotive force should have been induced. That is what you can understand. So here, in this case, an electromotive force has been created by the relative motion between the coil and the magnet. Such an electromotive force is known as an induced electromotive. So when the magnet and the coil get closer to each other or further away from each other, the magnetic field lines linked to the coil either increase or decrease. That is what is important. Magnetic field lines linked to the coil either increase or decrease. That is what I said, variation in the magnetic field lines. Since a deflection is observed in the galvanometer only at such instances. one can conclude that there must be a variation in the magnetic field lines linked to the coil in order to induce an electromotive force. So, this is what I explained to you all as well. So, I am sure you can understand that. There should be magnetic field, there should be motion, and due to this motion, there should be a variation in the magnetic field lines. Then only there will be electromotive force generated. With that, I'll move on to the next slide. And here you can see a larger deflection is observed in the galvanometer when the magnet is moved rapidly. So, this is also important, the last two steps. A larger deflection when the magnet is moved rapidly than when it is moved slowly, because the electromotive force induced in the coil is directly proportional to the rate of change of magnetic field lines. So, this is the second observation, understanding I told you all about. So, the electromotive force induced in the coil is directly proportional to the rate of change of magnetic field lines. When the rate of change is faster, the electromotive force is higher. When the rate of change is lesser, the electromotive force is also less. So, that is something you need to understand. So, with that, I'll move on to the next slide. So, based on that, if we try to understand, there are several factors affecting the magnitude of the induced electromotive force. So, several factors affecting the magnitude of the induced electromotive force. Faraday's experiments showed these factors, and there are three factors. We will try to understand them one by one. So, the factors that affect the magnitude of the induced electromotive force. Now, you can remember we had the coil. Now, when you increase the windings of the coil or the number of turns in the coil, then the electromotive force induced increases. That is one. Then in the activity, you all were able to see when we move the magnet faster, the deflection was higher. So, that means the speed of the motion of the magnet or the coil affects the induced electromotive force. And the third factor is the strength of the magnet. When the strength of the magnet increases also, the induced electromotive force increases. So, three factors that affect the induced electromotive force. So, first one, number of turns or windings I'll rewrite that. Number of turns or windings of the coil. Then we can say strength of the magnet. And finally, the speed of motion of the magnet or the coil. So, when we started the lesson also, when I started the chapter, you can remember students, in the introduction it was mentioned that either the magnet can be stationary and the conductor can move, or the conductor can be stationary and the magnet can move. Either way, there should be a relative change in the distance between the magnet and the conductor. So, then there will be induced electromotive force, induced EMF, that will give rise to induced current. That is why we call it as electromagnetic induction. And the induced electromotive force depends on all three factors: number of turns of or windings of the coil, strength of the magnet, and speed of the motion of the coil. When all of these increase, the induced electromotive force increases. That means the induced electromotive force is directly proportional to all of these factors. So here I will write that as a note. All the factors are directly proportional to the induced electromotive force. Now here also students, you all can see a similarity between this and the previous concept, where we had a conductor, current carrying conductor placed in a magnetic field, where when current flows through it, the force induced. That also depends on different factors. And there also all three factors were directly proportional to the magnitude of the force. Here, all the factors are directly proportional to the induced electromotive force. So, here it is actually the magnitude of the induced electromotive force. At the same time, now here also the induced electromotive force gives rise to a current flow. And the direction of the current flow depends on the direction of the magnetic field and the direction of the force, that is the movement. So there also we can predict or determine the direction of the current flow. For that, we have the Fleming's right-hand rule. Here you have to remember students, when it is electromagnetic induction, it is the right-hand rule. Fleming's right-hand rule. So we will use that to predict the direction of the current flow. So with that students, I am going to end this chapter, and in the next chapter, I will start by explaining the Fleming's right-hand rule, which is used to determine the direction of the current flow.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.